Hello. In this video, we are going to look at hypothesis tests for proportions, but this time with the claim that is more than, so that it becomes a right-tailed test. So here we have a random sample of 146 cars where 41 of them are white. And we want to use a hypothesis test to test the claim that more than 25% of cars are white. So first step, we write down our claim, and this is a greater than claim about a proportion. So we have P is greater than 0.25. Our null hypothesis then, a statement of equality, will be that P equals the 0.25. And the alternative hypothesis, H1, will end up being the claim P is greater than 0.25. We need to select our alpha, so we will use the 0.025 that we've been using. Now let's do our computations, and we'll start by computing P hat. So that equals 41 white cars out of a total of 146 cars. So 41 divided by 146. And we get about 28%, right? 28.082, 28%. Let's compute the standard error. So we have equals square root of 0.25 times, open parenthesis, 1 minus 0.25, close parenthesis, divided by the sample size, 146, close parenthesis. So that gives us a standard error of 0.0358. Now, let's use this information to find the p-value. Since this is a right-tailed test, and we want to find the area in a right tail using the norm dist, we are going to have to work with the complement and compute 1 minus the norm dist. So whenever you do a right-tailed test, which follows from a claim that contains more than or greater than, the greater than symbol, you will have to compute your p-value with the 1 minus norm dist. Our p hat represents the x. The value from the null hypothesis of 0.25 is our mean. Our standard deviation is the standard error, and cumulative is always true. We get a p-value of 0.19487, 195. And so when we do our decision, we see this is obviously greater than alpha. So the p-value is greater than alpha. So we do not reject the null hypothesis. So the conclusion, if we do not reject the null hypothesis, but instead support the null, then we are not supporting the claim because the alternative is the claim. So we get the sample data do not support the claim. And that claim is H1. Okay, so what you've noticed now, of course we've seen this before, when you have a p-value that's big, and big simply means bigger than alpha, we do not reject the null, so we do not support the alternative, which is the same as the claim. Now, let's go back and talk more about why we had to do this 1 minus. We've been using the norm.dist to do probabilities in left tails because the norm.dist always finds areas to the left of that first input you give it. So let's sketch again probability distribution of sample proportions. And right in the middle, is where we make our assumption, and this time we made our assumption that P is 0.25. We got a P hat here of a value of 0.28, which we can see is obviously greater than 0.25. Okay, so here is our computed sample proportion, P equals 0.28. So to find a p-value, we need to find the area in this right tail. But the norm dist, as is, if we just use a straight norm dist, the norm dist gives us this area to the left. Well, that's not what we want. It's the opposite of what we want. We want this area on the right. The area under the entire curve is 1, so we end up doing the 1 minus norm dist. So we have, we have to compute our p-value doing a 1 minus because the norm dist gives us area to the left. We are doing a right-tailed test where the area is on the right. So we have to take the area of the entire distribution, which is 1, and subtract what we don't want, which is the less than, denoted with the norm dist, and then we get what we do want by using the law of complements or the rule of complements. So the 1 minus was an example of using the rule of complements. All right, so that was an example of a greater than problem. Thank you for watching.